I want to maybe talk through a little bit of this section 8 2 example problems sheet that was linked in today's, uh, yesterday's Canvas page. And I may break it up into a couple parts so that there's not one giant long video, and you can then pick and choose what you want to watch at 1.5 speed or scroll through to get to kind of the important points quicker or whatever. So the kinematics of uniform circular motion, if you remember from back in chapter 4, the unit that you so fondly remember, a centripetal or a radial acceleration um, in that context was really, it was kinematics back there, and so it was just describing the motion instead of the reasons for it. And now in this unit, the reason that they're back to it is because now they're talking about the forces that actually cause circular motion to happen. And it's still uniform, meaning constant speed. Velocity is changing because it's changing direction as it curves around the circle, but constant speed. And later in this chapter, they'll get into non-uniform circular motion, where the rotating object starts to spin faster or slower with time. But the general kinematics equation for the radial or the centripetal acceleration is v squared over r. It's also, in terms of angular speed, omega squared r. It'd be good to look at why that is if you go back to chapter 4 or just Google uniform circular motion. You can see a million videos of teachers explaining that if you need to or want to. Remember that v is based on the distance around a circle, 2 pi r for circumference around the circle, divided by the time period it takes to do that. And so that can be substituted in for the v. And if you know radius and period and you don't know v directly, you can kind of work through it without having to go to the v first if you didn't want to. Why does it happen? It happens because there's no tangential force to speed it up. So v tangential is constant. Is constant because Newton's first law, basically. Or in this case, you can say that there's no tangential force to make it speed up. No net tangential force. Now we're going to get into the idea that there's a radial force, and that's what makes it change direction. So that's what makes it into a Newton's second law scenario, and that's why we're following the chapter on Newton's second and third law with this one now. So the stop and think thing in section 8.2, you can take a quick look at. I had to pause for a cough break, so sorry about that. I'm back, but the dynamics. Dynamics is the causes of motion. So we're in the unit on dynamics right now. If you look at the top of the pages in this chapter and in the Newton's Laws chapter, it'll say dynamics chapter 7 or dynamics chapter 8. Dynamics is why things do what they do in terms of the forces. And so now there is a net force that is toward the center of the circular path, and that does lead to the radial or the centripetal acceleration. So Newton's second law says we know F naught equals ma, and now we can say that Fc for centripetal equals ma centripetal, and that AC comes back to the beginning of it. And so you can substitute either v or r omega squared r or v squared r over r for MAC, depending on what variables you're given in any kind of problem. Stop and think, you can also kind of go back and look at. Remember, the answers to the stop and think questions are in the back of the chapter. after the last problems in the EMP section. So I will stop this video there and start a new one for example 3, and then another one for example 4, just so it's kind of broken up. I don't know if that's what people like or don't like, but sometimes longer videos people are telling me are difficult to stream, so I'll try to break things up that way.